wastewater from the building comes out into this manhole and goes into a pipe that goes out to a lift station that pumps the sewage out to the ponds. And so for this project, what we did is divert the sewage from this building, from this northbound comfort station. All the drainage from the toilets, urinals, sinks comes out here and gets diverted into our lift station, which is located over here, which has grinder pumps. And the grinder pumps pump the water underground over to our pilot treatment site in the back. After treatment at the pilot site, the water is returned back to the original lift station and gets pumped out to the ponds. So what we have is two separate water systems, and a lot of the rest areas, the comfort stations, are already plumbed this way. So we have a water system for flushing toilets and urinals, and a separate water system that's chlorinated for hand washing and drinking fountains. So this site already has a separated plumbing system. So this is the type of plumbing we need for going to do recycled water, that we want to put water that's not potable, basically either untreated groundwater or recycled water, into the non-potable system, use that for toilet and urinal flushing, and use the chlorinated well water for hand washing and drinking purposes.
So this is the return from our...
No, so this is this large pipe is for toilet flushing and urinal flushing only. It's untreated groundwater. And this, we could also put the recycled water into this pipe.
Oh, okay.
This upper pipe is for hand washing and drinking fountains, so potable. So basically, as a dual, we call this a dual plumbing system.
This is
so
the
one line
existing
for
condition.
non-potable and one for, yeah, and a lot of comfort stations are already this way, so they're already plumbed for recycled water effectively.
Okay.
So that's a real benefit, and we should take this into consideration when we're doing future designs, as this dual plumbing makes recycled water a possibility. So it's important. So here, what we have is wastewater coming from the building, going into our lift station that diverts it out. After it gets treated, it gets pumped over into the original existing lift station. And so this is where our diversion occurs at. So what we did is cut the pipe that goes over to that lift station and teed into it.
And the green pipe is the drainage pipe?
That is the drain that goes out to the original lift station.
Okay.
Yep. So this is raw sewage from the building. So it comes in. You can see what we have is a lot of trash that people throw down the drains. So there's a lot of rubber gloves and diapers and all kinds of plastic trash. So that's really problematic. And this is one of the challenges with wastewater from comfort stations, is that it's basically people use it like as a waste disposal system. They throw whatever they want in there. And so we have to have really good pumps, good grinder pumps, to be able to manage that material.
The pumping system is our system right now.
This is, yeah, so this whole lift station, this tank with the pumps and everything in here, is part of the pilot treatment system, because it's taking all the diverted sewage and putting it back to the wastewater system in the back, to our pilot system. So when we did the installation, the pipe that takes the water, the sewage, pumped from the lift station back to our pilot site was installed with an underground directional drilling rig. So basically what happened is they drilled a horizontal bore well from that lift station location under the concrete block wall that's over here, and we cut it on the other side, and then pulled the polyethylene pipe, a 2-inch polyethylene pipe, actually 4 2-inch polyethylene pipes, back through that borehole, through the underground borehole, and then connected it to our system at both ends. So basically it was very unintrusive way to install underground piping. We didn't have, there was no trenching, no excavation. We didn't have to damage the wall or anything. It was all able to do it underground.
So did you say 1 or 2 4-inch pipe?
There was 4 2-inch pipes.
4 2-inch pipes.
So 2 pipes to bring sewage over, because there's 2 pumps. So we have a redundancy there. 1 pipe to bring sewage back, and 1 pipe for a conduit for electrical.
It's all 2 inches.
All 2-inch pipes. So this
water
is
coming from...
Yeah, so water's coming from the comfort station into this tank where we're settling the solids out of the water and making the water clean enough for the second stage of treatment. So if you want to look in here, we can see all the solids that are accumulating. The solids are breaking down with bacteria that are in the water. And then we're spraying water in here to break the solids down further and help mix the system up. This tank has 5 compartments. So this is one compartment. It's about 6,000 gallons, so this is for storing all the solids. And then there's 4 small compartments where we flow the water from the bottom to the top of the tank and contact it with anaerobic bacteria to get better treatment. So we can look in here and see where the bacteria are growing in the water, and that the water is flowing from the top of this tank to the bottom of this tank and flowing through the bacteria that live on the bottom of the tank. There's sensors in here that measure the water temperature and also measure how much solids are in the tank, so we know when the tank needs to be cleaned out. And the last 2 compartments have a media, and the purpose of the media is to grow additional. That's better. So the purpose of the media is to grow bacteria, where we can contact the water with bacteria and get better treatment. So all this treatment happens with no aeration and no pumping. So this is all basically treatment we get with no oxygen. So when the water comes out of this tank, we're going to look at the vent. Okay. So this is a filter that filters the gases that come out of the tank. So it filters the methane and CO2 and any odor-causing gases that come out of the tank, and gets filtered through this bed of activated carbon, which absorbs the odor-causing gases, but also we think that there's some bacteria that grow in here called methanotrophs that would break the methane down into CO2. Effluent from the tank comes into this tank, which is a pump equalization tank. So what we have is pumps in here that pump the water into our treatment system. And when this tank is full, like if we get a lot of flow coming in, say for Thanksgiving, it overflows and goes into the old treatment system, the existing treatment system. And at night when we have no one using the facility, this allows us to keep running the treatment system at a constant flow rate until it pumps this tank all the way down. Take a look at what the effluent looks like that comes out of the tank. You can see it has a lot of dissolved organic matter and a lot of color. It looks like a brown color. And so this is the water that's going into our treatment system. And so this is all the stuff we need to remove from the water. Come around this way. So our biological process, the treatment process, basically has 3 steps. The first one is the backwashing filter. So this takes out all the organic matter from the water practically. And then we have a second stage process, another type of biological filter that takes out the rest of the organic matter and converts the ammonium into nitrate. And then a third stage, which is a sand filter, which takes out all the particulate matter. So if we want to look into each of these stages, the first one uses a sand pumice material, and so the water from that effluent tank is sprayed on the top, and the water that's sprayed on the top filters through that material, and bacteria that grow in that material remove the rest of the organic matter. I'm going to turn on the dosing so you can see it. So it doses every few minutes. And when the water filters through, it gets cleaned by filtering through this bacteria that grow on the media on this. This is the a second stage of another biofilter. So basically this uses a geotextile, and it has bacteria that grow on the geotextile. And this filter basically takes the effluent from the backwashing filter and removes some additional turbidity, some additional particulate matter, and also converts the ammonium into nitrate. So this is for nitrogen removal. The water from this filter gets pumped into the sand filters for final treatment before disinfection. So this acts to remove any additional floating material and take the dissolved organic matter to a much lower level and makes it so that our disinfection system works really well. So we can come and look at the sand filters. So these are called slow sand filters. And I guess we should mention that all the processes we're looking at we've selected for being the least maintenance, so the lowest maintenance and the most reliable performance. And so these sand filters basically just have a bed of sand. It's about 1 meter deep, and the water just slowly percolates through that sand bed, and as it percolates through, it gets contacted with bacteria that live on the sand, and they pull out additional dissolved organic matter and additional turbidity. We can look inside of these filters so we can see what it looks like. So we can come up and see the water filtering through the sand bed. So when the water comes out of this filter, the turbidity is very low, and it's in compliance with state recycling guidelines. So we've been getting turbidity about 0.5 and their requirements 2. So we're far below the requirement for turbidity removal. After we take out the particles, we take out all the fine material, the water gets pumped from this basin through the disinfection system. So disinfection here consists of ozone, UV, and chlorination. So the purpose of ozone is to take the color out of the water and to make the water basically crystal clear and make it easy to disinfect with UV and with chlorine. So ozone is generated inside of the building. It uses a 2-stage process. One stage pulls oxygen out of the air. The other stage converts the oxygen into ozone, and then the ozone is injected into the flow here. So when the pump turns on, it activates the ozone system to make ozone, and the ozone gets injected through this Venturi injector. The ozonated water goes through and it gets through a contact tank to give it time for the reaction to happen, and then a system to take any extra ozone that we don't need and get rid of it and burn it up. And then the ozone treated water gets pumped into a system with a UV lamp, and the UV lamp is inside the building. So this is the ozone generator. For reference, is a relatively small unit. This is enough to more than enough to treat all the water that we have here. This is the UV disinfection system. So this shines. This has a UV bulb in it, and the UV, when you expose bacteria that are in the water to UV energy, it makes it so that they can't grow anymore. And so this is a way to basically disinfect the water with no chemicals. Want to look at the panel now, or want to look at the chlorine?
So after ozone, it's going to the...
So after ozone and UV, so pretty much free of any viruses that are in the water, any bacteria. There's no issues with pathogens at this point, like all the water's been disinfected. Also, even the ozone helps break down chemicals that might be in the water, like there's pharmaceuticals or residual chemicals. Those also get broken down. So the water that comes out of the ozone and UV system is basically has been disinfected, and all the color has been removed, and it looks like drinking water again. But when we want to take the water and put it back into the building, we want to make sure that we're not growing bacteria in the pipes. So we add a small amount of chlorine to make sure that we're not going to have any bacteria growing in the plumbing system. And so the water after the ozone UV system comes into this tank and gets pumped through a series of tanks where we add a small amount of chlorine. And then the tanks are here for contact tanks to give the chlorine time to react with the water before it gets pumped back into the building. So right now we're running this system as a demonstration to make sure that all the systems are reliable and working properly. And the next step in this process would be to take the final water, which is located down here, and put this water back into the building for toilet and urinal flushing, or other non-potable uses. It could also be used for irrigation. And so you can see the water is very clear and fully disinfected, complies with all state requirements for recycled water, and then we call that tertiary disinfected effluent. We're also, as a part of this, we want to be able to monitor the system and make sure that it's working properly all the time. And so we have a series of sensors that continuously collect data, and these sensors collect data over here. It takes the final effluent and it measures how much oxidation has occurred in the water with this sensor called ORP. So this oxidation reduction potential, it tells us what the oxidation state is. We'd like this number to be high. It measures the turbidity that's in the water, how much particulate matter is left, and this is 0.56, 0.57, so that's a very good number. It measures how much chlorine is left in the water and the pH of the water, so those are numbers we want to know to make sure that we're in compliance with regulated chlorine levels. And this system continuously monitors the effluent quality and can send this data to a computer system or to a SCADA system, so we could be doing remote monitoring. So we could have the system running anywhere in the state and be collecting data on a computer either at a district office or at the headquarters office, and we would know the state of the water that's being produced continuously. So this is from the septic tank. You can see it has a yellow color with a lot of turbidity. This is a single pass through the backwashing filter. So the color is reduced and the turbidity is reduced. This is after the pack bed textile filter. So further reduction in turbidity down to close to 2. After the sand filter, so the color's been reduced even further and turbidity is less than 1. After ozonation, so the color's been removed and the turbidity is totally gone. Then after chlorination, so this is the final water that we propose to recycle.